皆様おはようございます。本日はITRIの AI やロボットで実現するスマート工場の未来オンラインフォーラムにご参加いただき誠にありがとうございます。本日の司会を務めさせていただきます翔と申します。ご覧の通り本日のアジェンダでは3名講師がそれぞれのトピックスを紹介します。各セッションでは10分間の Q&A 時間を設けてあります。ご質問がございましたらチャットにてご質問ください。アンケートの UR コードは右下にございますし、チャットでリンクも送付いたしますので、一部セッションだけ参加される方はぜひご意見やご感想をお聞かせください。ご協力いただけた方は本日のプレゼン資料をお送りいたします。さて、テストを行うためよろしければチャットにてスタンプやおはようなどをご投稿いただければ幸いです。ありがとうございます。ではオープニングとしてITRI MMSL の楊副所長並びにITRI日本事務所の楊代表からご挨拶を申し上げます。
Esteemed participants and distinguished guests, a warm welcome to today's online forum.My name is Bingxiang Yang, Deputy General Director of Mechanical and Mechatronic System Research Laboratories, MMSL at Industrial Technology Research Institute, or ITRI in Taiwan. We are delighted to have you join us as we embark on an exciting journey into the world's intelligent robotics and its transformative impact on manufacturing. In this dynamic era of Industrial 4.0, the fusion of robotics and artificial intelligence has changed the way we conceptualize, design, and operate our factories. The rise of intelligent robotics has opened infinite possibilities, empowering industries to enhance productivity, efficiency, and safety like never before. Throughout this forum, we will share our experience working with international partners in Horizon Europe's Hard2 project.And our contributions toward achieving flexible manufacturing with advanced AI-enabled robots. We will see how auto AI annotation and domain randomization approaches bring about VR and digital twin technologies which make meta factory possible. Lastly, we will delve into the most ingenious advancements in autonomous mobile robots or AMR technology.including industrial Mars and its target follower function, pick and place, robust localization, as well as extended applications into cleaning and art. Three researchers will share their insights, experience, and vision in their areas of expertise. I welcome you to ask questions during the Q&A at the end of each session.Your contributions are invaluable, and we believe that diverse perspectives will lead to innovative solutions and a deeper understanding of the potential unleashed by intelligent robotics. Before we begin today's agenda, I would like to first welcome International Affairs Officer and Representative of ITRI Japan, Martin Yang, for a few words.
皆さんおはようございます。ITRI国際提携担当役員兼日本事務所所長のヤンマーテンと申します。本日はITRI機械省のロボット専門家と、皆さんが集まって未来の工場製造技術発展模様を、議論するこのエキサイティングなイベントに参加できることをとても嬉しく思います。ご存知だと思いますが、ITRIは6000人以上の優秀な職員を擁する世界にも名乗りのある応用技術研究開発機関です。その使命は技術研究開発を通じて産業発展の推進、経済価値を創造、社会福祉を高めることです。私たちは高齢化社会、新しい生産、消費パターン、地球温暖化による気候変動、ポストコロナなど、グローバルな課題に直面する産業界とともに 新たな需要を見極めて、新たな価値を創造することに尽力しています。私はITRIの日本事務所所長を務めさせていただき、優秀なチームメイトのサポートに恵まれて、日本の革新なエコシステムと台湾のサプライチェーンを連結することに日々努力しています。両方の協力プラットフォームを構築することで、日本と台湾がより強く幅広い長期的な連携することを推進しています。ITRI日本事務所の手伝いによって、日体化により多くなコラボレーションができることを期待していますので、今後ともぜひ皆さんの力を借りてください。最後になりましたが、本日のイベントが円滑で成功に収めて、皆さんがますますご健勝であることを願って、私の挨拶を終わらせていただきます。ありがとうございました。
楊副所長と楊代表ありがとうございました。それでは最初の講師、Curtisさんからホライゾンヨーロッパプロジェクトについての経験をお話しいただきます。Curtisさん、お願いします。
Ladies and gentlemen, I'm Curtis Kuan from Industrial Technology Research Institute. Today, it is my pleasure to be here to share my experiences with you. In this presentation, I want to describe how we joined the Horizon Europe project, HARTU, related to flexible manufacturing with advanced AI-enabled robotics. This is a Horizon Europe project. We call it HARTU. Hope you will get something during this presentation. Thank you. First, here is the outline of today's presentation. First, a brief overview of ITRI Robotics is introduced. Then, how we joined the HARTU project, including the origin, the progress to HARTU, and what exactly HARTU is. Finally, a conclusion is provided. As we know, ITRI was founded in 1973. It's an independent nonprofit innovation institution in Taiwan. And our scope is developing technology for commercializations and nurturing opening innovation with academia, industry, and global partners. That is why I am here to introduce our global collaborations, especially with the European partners. And the other scope is incubating and spawning startups for emerging industries. And as we know, the most famous spin-off companies are TSMC and UMC in semiconductor areas. And ITRI has several offices around Taiwan and global branches in Tokyo, Japan, San Jose, Silicon Valley in the United States, and Berlin for the European business. And here is our basic information about ITRI. We have Tainan campus and the headquarters in Hsinchu and the Taichung campus. And we got many staff with PhD degrees, master degrees, and we have total patents around 32,000 and more. And this slide will introduce our robotics achievement in the past years. And for the future, we have robotic development in ITRI. We have core technology related to controllers that we call it I Can Think. The vision system for robotic system that we call I Can See. And the several applications, use cases in the practical industrial area. We call it I Can Walk, and the mobility, I Can Move. And for the I Can Think, we especially developed the robotic controller and the navigation algorithm and the simulators with EasySync and AsaSync. And the vision system is for the robotic system. We call it FOV vision, especially for object recognition and navigation. And I Can Walk, we have implemented several industrial applications, such as in aerospace manufacturing, drilling, or painting for the high-speed railway, and the grinding and the polish application for the semiconductor instrument, and the robotic weaving system for the composite material handling. And I Can Move, we have developed the dispatching system for multi-AMRs, and we have a fleet management software for AMR system. And this system right now is introduced to a semiconductor plant. Furthermore, we also have the medical robot is our focus as well, such as robotic bronchoscopy with diameter less than 3.5 millimeters. And here is our brief overview of our robotics achievement. Here, the next page, we want to say how we met Horizon Europe, HARTU. And I want to introduce the origin of the origin. From 2002 and 2003, we have joined the European project, we call it Muffins. This project is related to the multimedia processing in the Impact 21 environment. Here we can say ITRI is one of the partners, and the other partners are Imperial College in the United Kingdom and the IMEC for the Belgium, and the other partners from all over the European countries. And the other project from 2003 to 2005, and we got another partner from Switzerland. From this project before, based on our research capability in the past, almost 20 years ago, we joined these two projects. From these experiences with European partners such as Fraunhofer, Imperial College, IMEC, Vodafone, we have learned several lessons. The first one is the basic core concept idea is very critical. Use cases and the user scenario first. Then we, based on this user scenario and the requirement, we can implement the technology development. And diversity in the project partners. As we show, there are several various partners from the industries, including the universities, industrial company, and the academia research institution. So this diversity will bring the project different thinking logic and excellent sparkles during debate argument. And finally, we will get the consensus and the compromise from each other, and we will do our job or do our task, complete our task, what we have assigned, that we call it due diligence. And in these projects, they encourage participation in standardization activities and promote the achievement from the project to standardization organizations. So from these experiences, project achievement will be more applicable to the real and the practical use case in the industrial applications. That's why we have interest in joining the Horizon Europe project. So here is the slide showing our way to HARTU. In 2017, we, from the EU-Taiwan Industrial Policy Dialogue, we have decided we need to discuss on the AI robotics. EU and Taiwan agreed to focus on the development of AI plus robotics and start the preparation of robotics working group. And in 2019, we have established the EU-Taiwan Robotics Working Group. In this working group, we discuss the regulations, policies, and the joint research topics, especially on AI, data, and robotics. And this group is a established based on the consensus of European Commission Director Generals. For example, DG Grow, DG RTD, and the DG Connect, especially for the ICT technologies. Through 2020 to 2022, both sides of EU and Taiwan discussed the joint research topics, including the digital twin, human-robot collaborations, and AI robotics. And based on our consensus from both sides, in 2022, ITRI cooperated with the German AI Research Center, DFKI, and the Spain Research Institute, Technical, and the Philips Consumer Electronics, and the Turkey Automobile Company, forming a research consortium. We call it HARTU. And this project got approval by European Commission, and the project kicked off in this year, January. And in this project, there is a company from Taiwan, Infra, also joined this research consortium. So, what exactly HARTU is? HARTU means is the abbreviation from handling with AI enhanced robotics technology for flexible manufacturing. And as we described in the previous slide, there are several partners from all over the Europe countries, and 2 partners, including ITRI and Infra from Taiwan. So all partners are listed as this figure shows. And what HARTU is, we want to focus 5 use cases. The first one is the fixtures assembly, especially for the hand tool manufacturing. And here, this use case will be implemented by ITRI and the Infra, the Taiwan partners. And the second, the use case is the assembly for the consumer electronics. And this use case will be implemented by the Philips and the Technical. And this use case is from the Netherlands. And the logistics use case and the cart assembly transport, this use case is implemented from Technical and the TOFAS, the Turkey automobile manufacturer. And especially for the packaging use case, is about the food handling. It's implemented by the Italian partners, Poliva. And in this use case, we want to focus on how to grasp a workpiece, such as how to grasp the workpiece in the right position and the right orientation. So here we will handle various workpieces, such as hand tool, electronic components, foods and vegetables, and others. And from grasping, we need to assemble all the components into one product. So we need to handle the contact force, assembly procedure, and the accuracy, and the compliance between the workpiece and the adaptation to various workpieces with different size and weight. And finally, we have to put or place the assembled product into the right place. So we need to handle the position and how to package all the workpiece. So here is our scope for the HARTU project. And finally, here is a brief conclusion. From the slide before, HARTU is a real international research project with 6 countries without mother tongue as English. So participation in this project, we will learn how to cooperate with various countries from Germany, Spain, Italy, Netherlands, Turkey, and Taiwan. We will, as we said before, we have to achieve the consensus and comprise to each other and do the assignment work with the due diligence. And here is the reference for the Horizon Europe Cooperation Framework. The European Commission has assigned 95 billion budget for the research and the innovation activities. And one more slide for the Horizon Europe. We have in this Horizon Europe, there will 49 European partnerships, including several clusters. For example, health, digital, industry and space, climate, energy and mobility, food, bioeconomy and agriculture. And for us, we will pay more attention on the AI and the robotics. So here is for your reference. If you are interested in participating EU project, we can cooperate. Thank you.
カーティスさん、貴重な経験談をいただきありがとうございます。さて、今から Q&A 時間に入りますが、ご質問のある方はチャットにてもしくは挙手ボタンを押していただき、直接ご質問ください。はい、それではアンケートより頂戴したご質問から回答してまいります。Question 1. How AI can impact advanced manufacturing?
Yes, thank you everyone. So thank you everyone to join this seminar. So here I'm Curtis. I will answer the first question. How AI can impact advanced manufacturing. As we know, intelligence we mean is the capability to predict then how long the period we can forecast and how correct we can predict will be the indices we say someone has wisdom or not. Accordingly, AI is similar to the capability to determine the appropriate action under current state and based on the past experiences. That means if more data can be collected for AI learning, the capability of learning algorithm can extract insight from big data, and probably the correct prediction could be made. Applying this kind of concept to manufacturing, AI can be applied to deal with uncertainties during the manufacturing processes. So this is how AI can impact advanced manufacturing. Thank you.
我々の定義するインテリジェントとは予測する能力のことです。そしてどれだけ長い時間予測できるか、どれだけ正しく予測できるのかが、その人が知恵を持っているかどうかの指標になります。したがって AI は現状と過去の経験から適切な行動を判断する能力に似ています。つまり AI は学習のために多くのデータを収集することができれば、学習アルゴリズムの能力はビッグデータから洞察を引き出すことができ、そしておそらく正しい予測を行うことができるでしょう。このようなコンセプトを製造業に応用することで AI は製造工程における不可欠性に対処することができます。それでは Question 2. What you have learned from cooperation with EU?
Yes, for the second question, based on our experiences for cooperating with the EU partners, we have learned due diligence, compromise, and consensus. As I said during the presentation before, so we can have arguments during the design phase, then consensus can be achieved, followed by due diligence. We keep our promises to fulfill our responsibilities. So here is we have learned from the cooperation with EU. Thank you.
Due diligence 妥協、コンセンサスですかね。あと、設計段階で議論を交わして、コンセンサスを得た上で、 その後、デデューディスジェスを行って約束を守り、責任を果たすことです。皆さん、たくさんのご質問ありがとうございます。私どもも今後、さらなる協力を希望いたします。クルティクさん、ご回答いただきありがとうございます。お時間の関係で、その他のご質問は別途メールにて回答させていただきます。それでは次のセッションに移りたいと思います。講師のソルヒヨさんは、インテリジェントロボット、ビジョンシステムとメタファクトリーの開発についてお話しいただきます。では、ソルヒヨさん、お願いします。
Hi everyone, I'm Sergio. I am an engineer from the Robot Manufacturing Unit Department at ITRI. Today, I will talk about our intelligent robot vision systems and meta factory developments. I'm going to introduce to you two key products developed by our department, which are RobotTwin and FO Vision. Nowadays, in the context of global connectivity and increased demand for efficiency and an accelerated production pipeline, businesses are making their physical factories to be described entirely in terms of software. No matter where users are located around the world, with the aim of 3D digital environments, virtual reality deployment, and a communication scheme between digital and real assets, users can perform sensitive operations in the digital world and bring optimizations to the real world. This is the idea for MetaFactory, which serves as a realistic virtual environment replicating actual factory layouts, robotic cells, and workpieces. Along with virtual reality interaction, real manufacturing sites can be completely software-defined. As a result, users can navigate all the way through the virtual scene and test sensitive operations safely. More specifically, RobotTwin, as part of MetaFactory, intends to link motion commands between real-world and virtual scene. Users can deploy robot actions back and forth and collect relevant data from the real world to the virtual scene. The purpose of RobotTwin is to achieve capable human-machine cooperation by connecting VR equipment combined with high-fidelity physical engine from NVIDIA Omniverse, resulting in a human-machine mixed interactive simulation technology. Here we have one video. For instance, the user is wearing a VR headset and also grabbing a virtual stick. Using one of the VR controllers, making the virtual world follow the stick. This action is related to robot teaching. In another case, we have a user wearing a VR headset. Meanwhile, the virtual robot is performing defined motion commands and compounds of data coming from the real world in the form of images, and other graphics are projected into the virtual environment for the user's interest. RobotTwin comes with two operation modes. The first one is known as follow target mode. In this mode, the user grabs the virtual stick and the virtual robot will follow this tool in real time. Therefore, joint states will be shared to the real robot, resulting in real-time synchronization. Robot safety is also considered as well, along with a virtual reset option to prevent both robots from any undesired displacement. One more feature here is that 3D animations of the workers are included in the virtual scene to make the virtual reality experience more realistic. Let us now refer to RobotTwin's second mode, known as Play Mode. In this mode, virtual robot is given defined motion commands. Those are shared to the real robot to achieve real-time synchronization. At some point, data from the real robot is collected and projected into the virtual robot. This is all part of a loop to simulate a running production line. So now, let us proceed with our second product known as FO Vision. FO Vision mainly consists of three pieces of hardware, which are a 3D camera, a particular lighting source, and an edge computing device. The system will collect light-controlled 2D images along with 3D point cloud data to be processed by an embedded AI object recognition model. At the same time, the system will compute pickable points over the work pieces, and it will command the robot arm with inverse kinematics to perform pick and place operations. As a matter of fact, AI training for object recognition demands reasonable training datasets. Therefore, manual labeling can be tedious and time-consuming. In contrast, FO Vision offers a modeling and automated AI tool capable of mapping real-world 2D images into their workspace 3D CAD model representation. This tool not only enhances the realism of the virtual environment, but also automates the generation of annotated datasets, capturing pickable and unpickable points for each workpiece. To ensure that valid training dataset acquisition is doable, the AI annotation tool makes use of our domain randomization approach. In this way, several parameters will vary, such as workpiece posture and quantity, camera lighting and posture, light intensity and color rendering as well. So here we can observe how the algorithm makes the change in the beam color, and also the objects are placed randomly, and they all have variations which will make the training dataset stronger. So with all this being said, let us observe FO Vision deployment. Considering a real working environment, FO Vision collects data from a container loaded with metallic pipes and commands an industrial robot arm. The synthetic training dataset generated to train the embedded AI object recognition model proves to be valid in this case. So here we observe the objects loaded into the container, and then we can see the masks obtained by the AI object recognition model. And all of this is the result of the trained dataset, which has the variations mentioned before. So this is all for my presentation, and I thank you for your attention.
テルヒアさん、技術を分かりやすくご説明いただきありがとうございます。それでは Q&A 時間に入ります。Question 1. Do you consider safety for roboting?
Hi, thank you for this question. Yes, of course, we have included safety for this application. We can set up safety limits in the robot controller itself, and at the same time, we have included some programming functions in our virtual world application. So both real robot and virtual robot will stop if the user is pressing a button on the application. and we have also set some safety limits in the virtual world as well. So all is covered in terms of safety.
はい、もちろんです。ロボットが特定の空間から出ていくのを防ぐため、ロボットに安全制限を設定し、バックエンドもいくつかの安全機能も追加してすることで、ロボットが特定のスペースから動かないようにしています。実際のロボットおよび仮想ロボットも停止命令できます。さて、次の質問です。How to set up robot train?
Thank you for this question also. For this question, let me refer that we also follow the instructions given from the VR set maker, and at the same time we connect the robot to the PC by TCP/IP protocol. So this is quite a straightforward action. You will find it quite accessible to set up the system if you follow our example, which is using the UR10 robot and this HTC headset. In general, it is a very easy setup, and if you really need to ask questions, we are always ready to help you.
具体的な例を挙げますと、ユーザーはメーカーから提供される VR セットのセットアップ手順に従って、ロボットを PC ホストとインターネットを通信で接続する必要があります。一般的にセットアップは非常に簡単です。そろそろお時間も迫ってまいりましたので、その他のご質問は別途にてメール回答させていただきます。では、最後の講師、ホスウェさんは自律移動ロボットについてお話しいただきます。ホスウェさん、お願いします。
Hello everyone, my name is Josue. I'm the Deputy Technical Manager of the Service Robots Department, and today I'm going to give you a short presentation about the autonomous mobile robots that we have developed in our department. So my presentation is going to consist of two parts. First, I'm going to give you a short presentation of the intelligent AMR solutions that we have developed. And then in the second part, I'm going to show you some interesting applications where we combine robotics with arts. In our department, we have been developing autonomous mobile robots for quite some time, but we also have developed other type of robotic systems. For example, we develop a human-like robotic hand. And regarding the autonomous mobile robots, we have developed some mobile-based robots. And in this case, this mobile-based robot can carry 100 kilograms, but we have developed platforms for 250 kilograms, and we are hoping to develop soon platforms for up to 2 tons. And we also develop mobile armed robotic systems, like, for example, this robot here called Mars Lite. Now, in our intelligent AMR solutions, we need to integrate mobility, navigation, perception, manipulation in the case of mobile armed robots, and also human-machine interfaces to use these robots. And using all this integration, we can develop solutions for the industry. For example, the mobile armed robot here that we can use for pick-and-place applications, and other applications that requires the robot arm. We also have developed some applications for the autonomous forklift. For example, in this case, we developed a technology to perform the pick and place of a pallet. And we also have done some outdoors mobile robots where we use a robot to monitor an outdoors area for some companies. And in the case of service, we have also been developing technologies to be used in convenience store, hospital disinfection, and lobby cleaning. Now, for the case of the industrial applications, I'm going to give you the two short study cases. And the first one is the pick and place in a manufacturing cell. And as you can see in this video, this holonomic mobile manipulator is picking a workpiece from this manufacturing cell, and then it will place it in other locations around this manufacturing cell. This was done to mimic a real manufacturing cell where we have multiple processes that these workpieces have to go through. And this mobile manipulator will be in charge of moving around these workpieces. We also use the same mobile manipulator to perform other specific tasks. For example, here we have the LCD carrier polishing, where we use the mobile manipulator to approach this LCD carrier, and then we perform the polishing in 4 steps. And as you can see in this video, we're polishing the first quarter of this LCD carrier, and then the robot will move to the next, to the 3 other locations where we will perform the polishing task. For these industrial applications, we developed the following technologies. First, we develop a task manager and a task executor. The task manager will take the task one by one, and it will use the task executor to execute this task. And combining these technologies, we can do quick reprogramming of the robot. For example, we can change the arm trajectories, the mobile-based goal, docking operations, and other tasks. And this task definition uses a simple and intuitive XML format. So this is really easy to reprogram these robots using this task manager and task executor. And this task executor can also use relative reference frames. For example, in the 2 videos that I show you, we use April tags to reference how the movements are going to be done. And these 2 technologies are also easily adaptable to a dispatching system or a manufacturing and execution system using a task server, which leverages the task manager. Now, in the case of the service applications, we have the lobby cleaning, as you can see in the top left. This is an Ackerman type robot, and we use this cleaning robot. We adapt our technology to this existing cleaning robot to perform lobby cleaning. And in this case, you can see the robot is performing this cleaning trajectory that we computed based on the cleaning area that the user wants to do. We also have the hospital disinfection, which uses a similar technology where we can select the areas that we want the robot to clean, and then we can also select the areas that the robot should not go to. And this was already applied in the National Taiwan University Hospital here in Taiwan. The technology that we developed for these 2 service applications was a multi-area, multi-block cleaning path generation. Which this means that if you have a big map and you want to clean multiple areas, you can select these multiple areas one by one, and also select some blocks that you want this robot to go to. And then the robot will find the optimal path to move between these 2 areas. And we can also select the forbidden areas, which are the areas that we don't want the robot to go, maybe because we're doing some maintenance there or for any other reason. And we also develop an intuitive operation, which is an Android-based HMI, as you saw in the lobby cleaning case, where we have the screen to select the map that we want to use for this cleaning, or to select the task schedule or other tasks. And this selection of the allowed and forbidden areas can also be done through this HMI. And we can also generate the task schedule for all the tasks using the HMI. Now, we also have been doing some research to execute complex trajectories with mobile manipulators. And as you can see here in the top left, the robot is moving around this Lysagius path, and it's continuously tracking this trajectory while it moves. You can also see on this second example that the robot is following a sinusoidal path. Now, this type of trajectories can be used for certain applications where you actually want the mobile base and the robot arm to move continuously. A simple example is if you want to open a door, you might need to do this. You can do this step by step, first moving the platform and then moving the arm. But a more optimal way to do it is by coordinating the movement of both the arm and the platform to open the door. And the technologies that we develop in this case is the coordination of the robot arm, and in this case was a non-holonomic mobile base, but we can adapt for holonomic and non-holonomic. Just the non-holonomic case is more challenging, so that's why we work on it. We also had to do the redundancy resolution to execute these complex trajectories, because this is a 10 degrees robot, 10 degree of freedom robot arm. And because this is a highly redundant robot, we also need to consider the singularity avoidance to allow the robot to perform this task. We also included a self-collision and joint limit avoidance as constraints to execute all these paths. So in both videos, what you saw was the robot executing this task and continuously avoid the singularity and also continuously avoiding self-collisions and joint limits. Now, in the second part, as I say, we're going to show you some examples of how we combine robotics with arts. And in the first case study, we have the three-person project by the artist Tao Lueng. And this project was presented in the Patch Lab Digital Art Festival last year in Krakow, Poland. And in this case, what the artist requested from us is he wanted to use a VR headset that you can see on the top left video. And the headset is at the beginning showing a video that is the idea of this artist to show around the area where he's trapped right now, where he feels he's trapped because he can only see around. And then after this video finishes, we will see that the mobile manipulator on the top and the bottom left will start moving and tracking the movements of the headset. So what the artist requested is, can we follow the movements of the headset around this area? So he will walk around this area, as you will see in a couple of seconds. So as you will see here, once the video finishes on the top right corner, the mobile arm robot will start moving. And what you see right now on the top right is the stream of the camera mounted on the end effector of the robot arm. So right now, as the user is, in this case is the artist testing our project, is moving around this area, the mobile arm robot will follow his movements. So it will follow the movements of the head as well as his location around this area. And as you can see, on the stream, we're constantly streaming all the movements so that the user feels like it's actually in Taiwan. And this was recorded in a theater in Taipei, while, as I say, the user is in Poland, in another country. Now, for this specific case, we needed to develop an arm target follower. As you can see in this video, the arm is following the movements of the headset as the user moves around. And we also needed to develop a mobile-based target follower. And in this case, the mobile base needs to follow a target. And the arrow here is pointing to the direction that we have our target right now. And while it does so, we also have to consider there might be some obstacles around the environment, so it needs to avoid moving to those areas. Now, the technologies that we developed for this project was a remote control for the mobile arm robot. And as I told you, this is a remote control from a different country to Taiwan. And then we developed a smooth Cartesian velocity control for the 6 degrees of freedom robot arm, as you saw here with the movements of the arm. And this target follower also need to consider the constraints like joint limits and the workspace limitations. And for the mobile-based target follower, we included the collision detection, as I just mentioned. And all the execution that we performed was using the MQTT protocol. So this is how we receive the task from the headset to tell us where the mobile manipulator should go. Now, the second study case, we have this artist ask us to perform the movement of a mobile platform in this circular trajectory that you're seeing in this video. In this case, the robot must just move around this circular trajectory constantly while a performer is moving around it. And the challenges in this project were that first, that the lighting conditions change a lot. So we have really dark areas when the performer is moving around, and we also have really a lot of light in some areas. And this, as you can see here, the mobile base is already moving around this circle. And the problem was that because there's going to be, the audience is going to be seated around the performance area, there is no way to acquire features to actually localize the robot inside this circle. So the challenge was how we can actually develop some localization algorithm for the mobile platform so that it can move around accurately inside the circle. And as you can see here, the performance as it is moving around the circle, and we're showing some video through this transparent screen, the robot will keep moving around the circles with high precision. Now, for this specific case, we develop an indoor localization system that is robust to illumination changes. And we also develop a precise trajectory tracker for this mobile base. This is the end of my presentation. Thank you.
ハスウェイさん、大変興味深い話いただきありがとうございます。ここから Q&A 時間に入ります。同じく先ほどアンケートより頂戴したご質問から回答していきます。Question 1. How did you handle a delay between the user's movements and the robot's movements and still avoid conclusions in the three-person project?
Thanks for the question. So first, we developed this system with high priority for safety when the robot moves. So if the robots will stop if it receives a target position that can cause a collision with this environment and will warn the user about this limitation. And second, when we receive the target position message, we will filter this information over the last couple of messages, and we try to predict the next movement so that we can prevent collisions due to the transmission delay.
まず、ロボットが動く際の安全性を最優先して開発しました。ロボットが環境と衝突する可能性のある目標位置を受信した場合、ロボットの動きを停止し、その制限をユーザーに警告します。次に、目標位置のメッセージを受信した場合、その情報を過去数回のメッセージの中からフリーダーリングし、さらに次の未来の動きを予測することで、データのエンジンによる衝突を防ぐようにしました。Question 2. What impact do you think large language models could have on the field of mobile robotics?
I think that the large language models will have a large impact in the development of the human-robot communications for mobile robots. And having this natural language, using this natural language to command a mobile robot, I think it has is a useful feature that can be used in many applications. And this is especially the case for the service robots.
大規模言語モデルは近い将来、移動ロボットのための人間とロボットのイントラダクションの開発に大きな影響を与えると考えています。自然言語を使って移動ロボットに命令することで、複数のシナリオに適用できる便利な機能です。これは特にサービスロボットの場合です。ホスウェ、ご回答いただきありがとうございます。ご参加いただいた皆様と今後 AMR に関するコラボレーションができたら幸いに存じます。最後にクロージングとしてITRI MMSL 楊副所長から閉会のご挨拶を申し上げます。
As we conclude today's event, I thank you for being a part of this deeply insightful and enlightening online forum. Our collective passion for innovation and dedication to shaping the future manufacturing have made this an exceptional exchange. Through the experience of insights shared by our researchers and the thought-provoking questions raised by our enthusiastic audience, we have delved into the transformative power of intelligent robotics in driving the evolution of smart factories. We have witnessed how these cutting-edge technologies are revolutionizing production processes, enhancing efficiency, and ultimately paving the way for a more sustainable and competitive industrial landscape. Let us forum serve as a stepping stone towards forging new partnerships, fostering innovation, and nurturing the growth of intelligent robotics in the manufacturing sector. I encourage you to stay connected, continue to exchange ideas, and explore possibilities to collaborate. Once again, thank you all for the active participation, and I look forward to meeting you again in the future endeavors as we collectively shape the path to smarter and more prosperous factories.
以上をもちまして、AI やロボットで実現するスマート工場の未来オンラインフォーラムを終了とさせていただきます。最後までご参加いただき誠にありがとうございました。 アンケートの UR コードは右下にございます。皆様からのフィードバックを次回今後のフォーラムに生かしてまいりますので、ぜひご協力くださいませ。忌憚のないご意見をお待ちしております。ご参加いただき改めてお礼を申し上げます。ありがとうございました。